Okay, so on to example 4. Now we kind of discussed, composition. Now we're going to do it with some equations. And we're going to use the same equations that we did for our previous operations. And that's going to become helpful because then we're not going to have to redo our understanding of domain, but we are going to have to understand how the composition is going to affect our domain. So it says apply the composition of the two functions, then determine the domain. So immediately, first kind of thing I want to do is let's just talk about, let's write in the domains again so we don't forget about them. So our first two function, this is a linear function, and this is a quadratic function where the domain is unrestricted. So I'm just going to go ahead and write in our domain. Oh, well, let's go and see. I have 9 different examples we're going to work on. All right, cool. So let's go ahead and write in our domain. So for this linear function, that's going to be from -infinity to infinity. For the quadratic, that's -infinity to infinity. For h of x here, that's going to be from all positive values. So that's going to be 0 to infinity. And for j of x, that's going to be all values except -1/2. So that's going to be from -infinity to -1/2 union -1/2 to infinity. All right. So now let's go and look into g of f of x. Now, again, if you go back up to the notes that we provided at the beginning, you can see that this is the same representation of this, g of f of x. Okay? These mean the exact same thing. So basically what we're doing is we're taking our f of x function and we're going to plug it into our g of x function. Well, this one, f into h. Yeah, so basically what we're going to do then is we're going to take the g of x function and we're going to plug in f of x. I think I can fit it in there. So let's go and take a look at what that would look like. So if I take my g of x function and I plug in f of x's here, it's going to look like this. So it's going to look like f of x squared minus 4 times f of x plus 3. Right? Now, I'm only going to do this for like the first 2 examples so we kind of get a handle of it, and then we'll just kind of skip this step. But I just want you to see, this is just like the warm-up. On the warm-up, if we had a function, we just plugged it in, right? Just like any other input value. The difference is, in the warm-up, we didn't know what the function was that we were plugging in, so we just used function notation. In this example, we now know what f of x is. F of x is now defined as x minus 3. So now I can rewrite this with replacing f of x with what f of x is defined by, which is x minus 3. So I can now write x minus 3 squared minus 4 times x minus 3 plus 3. Okay? And now I just need to use a little bit of mathematical simplifying here to get this done. Now, x minus 3 squared, that is a binomial squared. I have already done some multiplying, so I'm going to do this one a little bit quicker. X minus 3, again, that produces a binomial squared, produce a perfect square trinomial. If you want to multiply this on the side, feel free to go ahead and do that, but the answer here is x squared minus 6x plus 9. I'll apply distributive property here, so that's going to be minus 4x. That becomes plus 12 plus 3. Okay, and now we just need to, combine our like terms. There's nothing here with x squared to add, but I have a negative 6x and a negative 4x, and I have a 9, a 12, and a 3 I combine. You can rearrange them, or you can just combine them from here. So my final answer is going to be x squared minus 10x. 9 plus 12 is 21, plus 3 is going to be 24. Okay, so you could write this as, the nice notation, g of f of x equals, x squared minus 10x, plus 24. And that'd be the nice, clean way to write the answer. Probably for time purposes and just for space, I'm probably not going to rewrite the original answer back up there. And maybe I'll, but just so you know, that'd be the, proper way to write in our answer. Now let's go ahead and look at our domain. So again, remember looking at the domain, we plugged in a function that was, defined for all values into another function that was defined for all values. And if we look at our final result of composition, we have another quadratic, so it's going to be defined for all values. So what you want to do when you're looking for the domain is look for the restrictions of the function that you're plugging into. That domain needs to follow, as well as your final result. Make sure that domain is going to follow, or make sure you can identify any restrictions there. And we'll get to a couple examples you'll see. But in this case, we have no restrictions. So my domain is going to be from negative infinity to infinity. Okay, let's go and look at the next example. And again, I'll kind of use the same notation just to kind of represent this. So now I'm plugging in f into h, right? So again, this is the same thing as h of f of x. Okay, so what we're going to do is we are going to plug in the f of x function into h of x. So here's h of x, and then here's f of x. So if I'm going to plug f of x, or let's see how that would look, it's basically going to be 3 square root of f of x. Well, we know what f of x is. F of x is x minus 3. So therefore, I can just rewrite this as 3 square root of x minus 3. Right? So there's your composition. That's h of f of x. So I can say h of f of x. Boom, done. Now let's go and look at the domain, because the domain has changed now, because I had no restrictions on my domain. When I was plugging it in. However, once I now plug it into my composition, you can see that I do have a domain restriction. And remember, under the radical has to be greater than or equal to 0. So now what I'm going to do is I'm just going to set x minus 3 greater than or equal to 0. And I could say x has to be greater than or equal to 3. So now my restriction of h of x, or of this composition, is now for all values that are greater than 3. So for the domain, I'm just going to write it can include 3, and then go all the way to infinity for all positive values. All right, so now let's get a little fun. Let's start working with some rational functions. Oh, I guess I like doing f, right? This will be my last one with f. So now let's go and plug in f of x, or f of x into j of x, right? I'll do this one last time. So again, just so you kind of get the hang of it. So now this is saying j of f of x, right? So now we're going to plug in f of x into j. So that's going to look like 2 over 2 times f of x plus 1. Well, we know, again, f of x is x minus 3, so then this would look like 2 over 2 times x minus 3 plus 1. And now we can just go ahead and simplify this, a little bit further here. That becomes 2x minus 6, applying distributive property here. So that becomes 2x minus 6 plus 1. And then my final result here is 2 over 2x minus 5. Okay, so now let's go into our domain. So again, we're plugging in f of x, which is defined for all values. But once we plug it into our composition, we now have a new restriction on our domain. Because remember, the domain of a rational function says, it's true for all values except for the values that make the denominator equal to 0. So we need to find those undefined values. So I'm simply going to take my denominator, and set it equal to 0. When I add the 5, divide by 2, I get x equals 5 halves. So what I notice is when x is equal to 5 halves, when I plug in 5 halves here, 2's divide out, 5 minus 5 is 0, I get 0 in my denominator. So x equals 5 halves is not defined in my function. So therefore, my domain is going to be from negative infinity to 5 halves union 5 halves to infinity. So it's true for all values except for 5 halves. And again, that's just going to be the interval notation. But it's true for all values except for 5 halves. All right, so now let's go and get into j of h of x. So now we're going to take our h of x function and we're going to be plugging it into j of x. So I'm just going to hop now right into it because we kind of already have, we know our functions. So I'm just going to, start plugging them into each. I'm just going to plug them in. I'm not going to show the steps like I did up above. So h of x is 3 square root of 2. So this becomes 2 over 2 times 3 square root of 2. And that was plus 1. Okay, so that is my h of x being plugged into my j of x. Now I just need to simplify this. Make sure when you're distributing this here that you only multiply the 2 times the 3. You can't multiply the 2 inside the radical. But as far as the composition, simplifying the composition, it's pretty clear cut here. I didn't want to do this in pink. I wanted to change this over. So now I got to go to red for my domain. But everything looks here pretty good, right? But we can see here that I now have some restrictions, a new restriction on my domain. There's really nothing else I can do to simplify this. I could rationalize the radical if I wanted to, but again, that's going to produce a different result, right? So if you're doing like a multiple choice answer and you need to rationalize the radical, there was no radical in the denominator, just remember that you can multiply by the conjugate on the top and the bottom. But again, that's not really the purpose of this video, because we're just looking for the domain, right? And this is simplified enough for me. We do times when we want to rationalize the radical, but for right now, I'm not concerned about that. I'm concerned about, what are the values that are not going to be in the domain? And again, just like our last example, we know that where'd my... h of x. Oh, I'm sorry, that's 3 square root of x. I was wondering, I'm like, what happened here? Okay, so that's 3 square root of x. I was like, something's weird's going on. So this becomes 6 square root of x. Sorry about that. Plus 1. Okay, so then you rationalize radical. It'd still be the same thing, but x is under your radical, not 2. So I was kind of getting a little crazy there. But anyways, we need to figure out what values make this denominator equal to 0. So again, let's set it equal to 0. So that is our final result. You could simplify it by rationalizing the radical, as I mentioned. But let's go ahead and solve this. 6 square root of x, plus 1 equals 0. Let's find the values that make this 0. So subtract 1. 6 square root of x equals -1. Let's see, divide by 6, square root of x equals -1 over 6. And now I need to get rid of the square root, so I'm going to square both sides. And what I get is x equals 1/6. Oops, I'm sorry. X equals 1 over 36. Right? Because -1/6 squared is, basically -1/6 times -1/6, which is a positive 1 over 36. And we want to be able to determine, does that work? Can we plug that into our equation or our new function? Is that going to make our denominator 0? And if you look at that, the square root of 1 over 36 is going to be 1/6. Square root of 1 over 36 is going to be 1/6, and that's going to be 1/36. And 1/36 times 6 is going to be 1, but 1 plus 1 is 2. So guess what? This is not going to be undefined, at least for that value. So therefore, it is defined for the value of 1 over 36. Oh, and I forgot to mention, I got carried away because I made that mistake. So we don't need to worry about this new restriction here. It is value for 1 over 36. And the reason being is if you look at the radical, we have another radical constraint from our h of x. Remember, our h of x is for all values that are greater than 0, right? Because for you to take the square root of a radical number, it has to be greater than 0. So if I look at this, my domain, if I just take my original restriction from 0 to infinity, well, first of all, that means all values inside the radical are going to be evaluated. And then if we look at this constraint, 1 over 36 is contained in this domain. And again, when we plug in 1 over 36, it does work, right? It doesn't make the denominator equal to 0. So we're fine. So the domain of this function is just going to be from 0 to infinity. So again, look at the domain of the function that you're plugging into. Make sure you have that domain. And then also, once you have the composition, make sure that you are evaluating to see any domain restrictions there. All right, so now let's go and plug in g of x into h of x. All right, so h of x, x squared minus 4x plus 3. So in this case, I'm going to have, let's see, that's 3 square root of x squared minus 4x plus 3. Okay, so that is our function. Really not much else we can do to simplify this. Now we need to go ahead and determine, well, all right, so then what is the domain? Well, x squared minus 4x plus 3 in itself is defined for all values, but once we put it under a radical, we know it's only defined for values that are greater than or equal to 0. So now what I need to do is I need to set this as an expression, x squared minus 4x. Oh, let's do the domain in a different color so we know we're kind of done. Okay, so if I want to find the domain here, I'm going to do x squared minus 4x plus 3 is greater than or equal to 0. Well, I can factor this. So by factoring this, I get x minus 3 times x minus 1 is greater than or equal to 0. Now what we kind of need to do is kind of understand when is this graph going to be greater than 0. We don't want to set both of these as like the zero product property, both of these equal to them. What we want to do is kind of understand a little bit when are the values going to be greater than 0 or not. So the easiest way, fastest way that I've looked at this is just looking at this graph. If I have x minus 3 and x minus 1 as my function, these are going to be the zeros or the x-intercepts of the graph, right? Those are going to be the solutions. If I had this as x minus 3 times x minus 1 equals 0, those are going to be my x-intercepts. Also, since my 1 is a positive, I know that the graph is going to be opening up. So the graph is going to look something like this. Let's see, that's at 1 and at 3, right? So the graph is going to cross at 1 and 3. And I know the parabola opens up. So now for what values, what x values is my h of x going to be, under my radical is going to be, greater than 0, right? And what you can see for all x values less than -1 and for all x values greater than 3, I am going to produce that result. So my domain is going to be for, well, let's go and double check. Let's make sure that works. So let's plug in 0. So if I plug in 0 here, I get -3 times 0 minus 1, that's -1. -3 times -1 is going to be, obviously, positive 3, which is greater than 0. Then let's pick another number like 4. So if I plug in 4, I have 4 minus 3 is 1. 4 minus 1 is 3. So I'd have 1 times 3, which is greater than 0. And then let's plug in a number like 2 and see what happens there. 2 minus 3 is -1. 2 minus 1 is 1. So -1 times 1 is -1, which is obviously less than 0. So it doesn't work. So it's only going to be values from -infinity to 1, including 1. 1 works. Union 3 to infinity. Okay, so here is another example of taking a quadratic under a radical and just kind of understanding it by using, a graphical method. Understanding the intercepts and understanding the shape of the graph. All right, so now let's go and plug in J into G. This one does not look like that much fun, but that's okay. We'll go ahead and plug it in. So let me just remind myself here. So I basically have J of x squared minus 4 times J of x plus 3. Okay, all right. So J of x is 2 divided by 2x plus 1. Yeah, okay. So this is going to equal 2 divided by 2x plus 1, squaring that, minus 4 times 2 over 2x plus 1, and then plus 3. Whew. Okay, so there are some things we could, simplify to this. Let's go and look at the initial conditions here first to kind of see, what's really going on. So from J of x, we know that the domain of J of x is for all values except for -1/2. And once I plug that into my function G of x, you notice that that does not change. Like there's no new restrictions. Like here, when I added in my G of x into H, I had a new restriction because it was under the radical. Here, by adding J into G, I'm not adding in any new restrictions. The same restrictions are going to apply that the denominator cannot equal -1/2. Doesn't matter if it's squared or not, the denominator cannot equal -1/2. So I'm just going to kind of stop right here, and I'm just going to say the domain is the same thing as J of x. -1/2 union -1/2 times infinity. Now, as far as simplifying this, I mean, that really kind of just depends on, what your teacher expects from you, or if it's like a multiple choice question and so forth. We can obviously just kind of rewrite this, and then if we wanted to get common denominators, we could do that, and I'll kind of see how far I want to go. So if we squared this, though, we would get, 4 over 2x plus 1 squared minus 8 over 2x plus 1, and then plus 3. And then obviously if I wanted to, combine these, then I could get common denominators, and the common denominator would be 2x plus 1 squared. So I need to multiply this by, 2x plus 1, and multiply this by 2x plus 1. And then over here I need to multiply by 2x plus 1 over 2x plus 1. And this is going to be a little bit more math. I don't want this video to take too long, but I'll at least write it under one common denominator. And then obviously if you would need to be doing the math, you can go ahead and finish it. But I still have 3 more examples, so I don't want to cover this too much. So I do 4 minus 8 times 2x plus 1 plus 3 times 2x plus 1. Oh, I'm sorry, that's squared. And that would all be over my common denominator, 2x plus 1 squared. So a lot of times, we look for the this to be simplified, and you could further result this. You just multiply this by distributive property. You would need to expand this and then multiply by 3, and then go ahead and combine all of your like terms. And I'll probably provide at least maybe the answer on my finalized sheet, but I'll save it for the video. All right, so f of h of x. So now we're going to take h of x, plug it into f of x. So let's see, h of x is 3 radical 2, or 3 radical x. I don't know why I was doing that. So this is basically going to be 3 radical x, and then minus 3. So here, you can see this one's rather simple. There's really nothing else I could do simplifying it. And my domain is basically the same as originally h of x. So my domain here is going to be 0 to infinity. There's really nothing else. I could factor out a 3, I guess, if you wanted to. We could make this maybe a little bit nicer by factoring out a 3. But still, the domain is not going to be unchanged. So now let's go and plug in h of x, or j of x, into h of x. Now this one kind of gets a little interesting here, because we're going to have 3 square root of now what j of x is, which is 2 divided by 2 x, forgot j of x, minus 1. Okay, so what are we going to do here? So we noticed that for j of x, we had a previous restriction, x could not equal -1/2. Now we're putting it under a radical. So now we know that under a radical, it has to be all positive values. So before I go ahead and look into my domain, I'm probably going to want to simplify this. And remember, one of the rules of radicals, if you have a radical a over b, then you could rewrite that as radical a over radical b. So I'm going to go ahead and do that. I'm going to put the 3 up top because it's really 3 over 1. So I'm going to rewrite this as 3 radical 2 over square root of 2x minus 1. So what this allows me to do is see that, all right, I know that -1/2 doesn't work because -1/2 makes my denominator 0. And even though I can take the square root of -1/2, I know that when you take the square root of 0, you can take the square root of 0, but the problem is that the square root is in the denominator, so it makes the denominator 0. So -1/2 is not defined. So I'm just going to kind of write that as a little side note. X cannot equal -1/2. Cool, I understand that. But we see that we entered this into a radical, so now we need to take into consideration the constraint of the radical, which is all values under the radical, or we need to place values that are going to make the radical greater than or equal to 0. So now I need to take 2x minus 1 and set it greater than or equal to 0 and go ahead and solve. So in this case, by adding 1 and dividing by 2, I have x is greater than or equal to 1/2. So what this is saying is x has to be, oh crap, that's supposed to be +1. I wrote that wrong. Good catch. +1. That's +1. So that's a minus. X cannot equal, yeah, I was like, I remembered the solution, but I forgot around. So, all right, so x has to be greater than or equal to -1/2. But again, remember, x cannot equal -1/2. So my domain is going to be written like this. Domain is going to be parentheses now. Rather than using the brackets, it's going to be parentheses -1/2, and it's all values greater than -1/2, so that's going to go towards infinity. Okay? All right, last but not least for example number 4. Here is a function evaluated into another function. And it kind of looks funny, but if you just really sit down and say, all right, let's just follow the same process. What does, again, what does this mean? This means f of x. Okay, so you're going to take your f of x, which is x minus 3, and you're going to plug in f of x. All right, so what does f of x equal? F of x equals x minus 3. Okay, so we don't really need the parentheses. Interesting. Okay, it wasn't as bad, right? It looks funny, but it's really not that bad. And we can see, obviously, f of x is defined for all values. When we plug it in, we're still defined for all values. So my domain in this case is going to be from negative infinity to infinity. So there you go, ladies and gentlemen. That is how you evaluate, or I'm sorry, not evaluate, but you provide the composition of two functions, as well as go ahead and identify the domains. And again, remember the key aspects here is understanding what the domains are of your function, taking that domain when you plug it in, so make sure whatever the input is, that's the second function that's listed, or the input function, make sure you take that domain restriction with it. And then obviously once you've applied the composition, sometimes you're going to have new restrictions, sometimes you won't, right? I mean, here we had no new restrictions, but when we place it like under a radical, or when we place it with a rational function, you'll see that there's going to be new domain restrictions. So just make sure that you are aware of those. So now it's on to the next example.